All right, so chapter 4 is about trigonometric functions. We are integrating section 4.1 into section 4.2. So starting on page 103 of your notes packets, trigonometric functions of acute angles. Some key vocabulary to know is acute, meaning a less than 90-degree angle. Similar, referring to two shapes that have the same shape but might have different sizes. And then right triangles, which is a triangle with one right angle. We're going to start by defining the 6 trigonometric functions for an acute angle. So let theta be an acute angle in the right triangle ABC. So let's draw a diagram of a right triangle with an acute angle theta called ABC. If this is our theta, then this is the side that is opposite of our angle. This is the side that is adjacent to our angle, and this is our hypotenuse. All right, so our first function that we'll define is sine. Now sine is a function, so it takes an argument. The argument of this function is an angle theta. We could abbreviate this sin theta, and that is defined as opposite over hypotenuse. All right, our next angle, or our next function that we'll define is cosine of theta, abbreviated cos theta, equals, this is adjacent over hypotenuse, and tangent of theta, or tan theta, which is opposite over adjacent. And then we have cosecant of theta, abbreviated CSC theta, which is hypotenuse over opposite, secant of theta, or SEC theta, which equals hypotenuse over adjacent, and finally cotangent of theta, abbreviated COT theta, equals adjacent over opposite. The two most common triangles that we will use these values from are the 45-45-90 triangle, or the isosceles right triangle, and the 30-60-90 triangle, which is half of an equilateral triangle. First, we'll look at the 6 trigonometric values for an angle of 45 degrees. Since it's the 45-degree angle, I know we're working with an isosceles right triangle. So we can draw here a triangle that has a right angle, and I know that both legs are the same length, which makes this a 45-degree angle. We can select to have the legs be a length of 1, and then we need to find the length of the hypotenuse. So using the Pythagorean theorem, I can say a squared plus b squared equals c squared. Each of my legs has a length of 1, and I'm looking for the length of the hypotenuse. 1 squared is 1. 1 plus 1 is c squared. So 2 equals c squared. Then c equals the square root of 2. I only have to take the positive value for square root of 2 because this is a distance. So now I know that my hypotenuse has a length of square root of 2. Now we can use the definitions from above to find sine of 45 degrees, which is opposite over hypotenuse. So looking at our angle, opposite is 1 over the hypotenuse is the square root of 2. We don't want to leave a radical in the denominator, so to rationalize this, we multiply by the square root of 2 divided by the square root of 2 to get the square root of 2 divided by 2. We'll do a similar thing for cosine of 45 degrees. Cosine is adjacent over hypotenuse. The adjacent side is 1 divided by the square root of 2. We already know that when we rationalize it, we will have an answer of the square root of 2 over 2. Tangent of 45 degrees. Tangent is opposite over adjacent. Opposite is 1, adjacent is 1, so we have 1 over 1, which can be simplified to 1. Scoot this down a little. Our next function is cosecant of 45 degrees, which is hypotenuse over opposite. Our hypotenuse is the square root of 2. Opposite is 1, so we have a value of the square root of 2. Then secant of 45 degrees, which is hypotenuse over adjacent. Again, we have the square root of 2 over 1, which is the square root of 2. And finally, we have cotangent of 45 degrees, which is adjacent over opposite. The adjacent side is 1, the opposite side is 1. So again, we get 1 over 1, which is 1. Our final answers can be boxed here. There are 6 trigonometric functions, so we have a total of 6 answers for this problem. And I will highlight them as well to make them more visible. All right, for example 2, you follow the same process with a 30-degree angle. So this is the other common triangle that we see, the 30, 60, 90 triangle. Start by drawing a sketch of your triangle, finding the length of all 3 sides, and then you can go ahead and find the 6 trigonometric function values. Okay, going on to example 3 on the next page, we want theta to be an acute angle such that sine of theta is 5/6, and we want to find the other 5 trigonometric function values of theta. So let's start by sketching our triangle. We know that it's a right triangle because we're using the trigonometric functions. Theta is acute, so let's put it here. We know that sine of theta is 5/6. Recall that sine is opposite over hypotenuse. So that means our opposite side could be 5 with a hypotenuse of 6. Using the Pythagorean theorem, we can find our last side. So we would say a squared plus b squared equals c squared. A squared plus 5 squared equals 6 squared. A squared plus 25 is 36. Subtracting 25 from both sides, a squared is 11. Then a is the square root of 11. Again, we're only interested in the positive square root because this is a distance. So our distance here, the length of our second leg, is the square root of 11. So now we can find the remaining trigonometric functions. Cosine of theta was adjacent over hypotenuse, so adjacent is square root of 11 divided by our hypotenuse is 6. Notice this is already rationalized, so we don't need to simplify any further. Tangent of theta, which is opposite over adjacent. Opposite is 5 over adjacent, which is the square root of 11. This does need to be rationalized, so we multiply by the square root of 11 divided by the square root of 11 to get 5 times the square root of 11 over 11. 5 and 11 have no common factors, so this is already simplified. Then we'll go cosecant of theta. Cosecant of theta is hypotenuse over opposite, so we have 6 over 5. Secant of theta, which is hypotenuse over adjacent, so 6 divided by the square root of 11. And finally, cotangent of theta, secant of theta should be rationalized, square root of 11 divided by the square root of 11. So we have 6 times the square root of 11 over 11. And cotangent of theta, which is adjacent over opposite, which is the square root of 11 over 5. Again, I'll go through and box our final answers. Since sine was given to us, we only have 5 new values for our final answer. All right, next we are evaluating functions without using a calculator. So this is similar to what we did in example 1 and 2. Secant of 45 degrees is actually from example 1, but let's look at it again. If our angle is 45 degrees, then we create a right triangle where our angle is 45 degrees. Remember, this means you have a 45-90 triangle. So we have our legs that are each a length of 1, and our hypotenuse is a length of the square root of 2. Secant of 45 degrees was defined as hypotenuse over adjacent. So secant 45 degrees equals the square root of 2 over 1, or the square root of 2. You'll do a similar process for sine of 60 degrees. We'll go ahead and skip that one and look at cosecant of pi over 3. Now notice there's no degree symbol. So that means that the unit that we're working with here for measuring that angle is radians. So now we're looking at a triangle, right triangle, with an angle measure of pi over 3 radians. That means our other angle here is pi over 6 radians. If you'll recall, pi over 3 radians is equivalent to 60 degrees, and pi over 6 radians is equivalent to 30 degrees. So this is a 30, 60, 90 right triangle. Okay, so if we label our sides of the triangle here, I know that this leg is 1 and this hypotenuse is 2 because this is half of an equilateral triangle, and that makes this other leg have a length of the square root of 3 found by the Pythagorean theorem. Cosecant of pi over 3 was defined as hypotenuse over opposite. So we can calculate that cosecant of pi over 3 is equal to 2 over the square root of 3, which rationalized is 2 times the square root of 3 over 3. And you'll follow the same procedure to find tangent of pi over 3. Next, we're evaluating using a calculator. So on your calculator, you'll go to, let's notice that you have the trigonometric functions. You need to make sure that you're in the correct mode. So in this case, making sure that I am in degrees. So notice here I'm in degrees, and then I can do the calculation, which is sine of 74. So sine of 74 degrees is 0.961, rounded to 3 decimal places. So I'll put here equals 0.961. And the next 3 are calculated the same way, verifying that for the last 2 you are in radians instead of degrees. On the next page, for example 6, we are looking to find the angle that satisfies the given equation. So now we're looking for the angle. We can again draw our triangle with theta. We know it's a right triangle. Sine is opposite over hypotenuse. So we have opposite and hypotenuse, and we need to find this angle. The way we can do this is by using the Pythagorean theorem to find our missing leg, or recognizing this pattern as a 30, 60, 90 right triangle. Okay, so once you have this pattern, you know that your angle theta is 30 degrees or pi over 6 radians. All right, the other three are left as an exercise. All right, for example 7, we're looking at a right triangle with a hypotenuse of 8 and a 37-degree angle. So if we draw our triangle, we know it's a right triangle. Our angle is 37 degrees and a hypotenuse of 8. What can we find out? Well, we know that the internal angles of a triangle have to add up to 180 degrees. So that means that this angle has to be 53 degrees. And then we can use our trigonometric functions. So if I'm looking for, let's call 37 degrees the angle that we are using, this would be our opposite. This is our adjacent. So I can say I know our degree and I know our hypotenuse. So if I use sine of 37 degrees would be opposite over 8, multiplying both sides by 8. I know that opposite equals sine of 37 degrees times 8. Using our calculator, we can find that that value is 4.815. Similarly, we can use cosine to find the adjacent value. So we would say cosine of 37 degrees equals adjacent over hypotenuse, multiplying both sides by 8. Then the adjacent side length is cosine of 37 degrees times 8. Using our calculator, we can find that this is 6.389. If you are finding different values with your calculator, make sure that your settings are set to degrees and not radians. In the final example, we are using the same tactic as we saw in example 8. We have a triangle that is 65-degree angle and 340 feet for one of the legs, and we want to find the other leg. So we ask ourselves, what function do we know that has an angle and 2 legs? So I can think that tangent of 65 degrees would be opposite over hypotenuse. Now opposite is called h, over adjacent is 340 feet. So multiplying both sides by 340, we can find that h equals 340 times tangent of 65 degrees. And using our calculator, we can find that this is 729.132. Again, make sure your settings are set to degrees and not radians for this calculation. We can double check and say, does this answer make sense? Because this is a 65-degree angle, we know that this is a 25-degree angle, so we would expect the building to be much taller than 340 feet, so this answer does make sense. Okay, this is the end of section 4.2, so take a few minutes to think about what you learned in section 4.2 and jot down a summary in this box.